Good evening. I'm Steve Erickson of the Geological Society of Minnesota. The GSM has been in existence since 1938 and offers free lectures at the University of Minnesota to the general public about topics in the earth sciences. Please see our website at www.gsmn.org for a complete lecture schedule. Since the COVID shutdowns in 2020, we've started offering Zoom lectures, which allows us to connect with speakers from around the country. Many of these lectures have been recorded and are available on our YouTube channel. Search for Geological Society of Minnesota on the YouTube website. Tonight we're joined by Dr. Timothy McMahon from the Jackson School of Geology, actually the Bureau of Economic Geology, University of Texas, which is associated with the Jackson School of Geology at University of Texas. Prior to joining the BEG in 2022, Tim spent most of his 25 years as a geologist in the oil and gas industry, including 10 years with ConocoPhillips, mostly as an exploration geoscientist. He has worked on projects around the world and lived in Canada, Norway, and Malaysia. After leaving ConocoPhillips, he founded Cutlass Exploration, where he participated in onshore U.S. exploration wells and provided geoscience consulting around play-based exploration, resource assessment, and application of machine learning to geological problems. He received the BA in geology from Rutgers, an MS from NMSU, and a Ph.D. from the UT Austin. Please welcome Timothy McMahon.
Put out this past August. It's a overview of shale plays in the U.S. This is an open access article, so anybody who's interested can get it. And if you think you might be interested, I will have a URL or a code up at the end of the talk that you can just copy and link to it. I'm going to just back out because you guys are up in the land of Precambrian rocks and things like that, and just talk a little bit about shale, or what we tend to call mud rock is a more generic. So it's a fine-grained sedimentary rock, less than 0.004 millimeters in terms of grain size. It may be fissile, which is an actual shale, or it could be massive, which are sometimes called mudstones. We tend to use mud rocks as a sort of catch-all for shales and mud rocks of any composition. So it may be clastic or carbonate. These are generally deposited in low-energy environments, lakes, lagoons, or deep marine settings. In terms of conventional oil exploration, it acts as a seal that holds the hydrocarbons in, or as a source rock, and I'll talk a little bit more about that in a second. In unconventional exploration, it acts as a reservoir and a source rock. So when I talk about source rock, when you get hydrocarbons, you need to have some sort of source of organic carbon. Contrary to popular belief, this does not come from dinosaurs. The most common are plankton and algae in the marine setting. You can have algae from lakes, green pond scum effectively. There's a very good source rock as well. And then land plants. Now there's different types of source rocks. These plankton and algae tend to be sort of this type 1 or type 2, which generally means that they just will create oil when they come along. Land plants tend to be more of a type 3, which regardless of what happens is probably going to be more prone to generating natural gas. And then they have something that sits in between the type 2 and type 3 that may have a mix of these marine and land plant carbon sources. So what happens is dead plankton, algae, are floating in the water column. They start dropping out as they die. So does clay and plant material brought in by rivers or streams. So these will then settle down in these low energy environments on the bottom of the ocean or on a lake. And that gives us these black looking shales here. This is in Western Ireland with a Coke bottle for scale. So these black shales are what a typical source rock looks like. I already said that. Now, as you bury this mud at the bottom of the ocean, it compresses into this shale, And this is the most common type of source rock we see in the oil industry. Now, when you start burying these things, there's a geothermal gradient. The earth gets hotter as you go down. Certainly in the crust, this is due to mostly radioactive decay of uranium and other radioactive elements. And as it compacts and the temperature starts going up, when you hit 60 degrees centigrade, you start generating hydrocarbons from the organic carbon that's in the rocks. So 60 degrees to 160 degrees is considered the oil window. This is where you're going to be generating oil if you have an oil-prone source rock. You could be generating gas if you have a gas-prone source rock. Once you hit about 160 degrees centigrade, you're going to start generating natural gas regardless of the source rock. It's hot enough that it starts breaking down the oil into gas. And as you get above about 225 degrees, you lose the natural gas. It's too hot to keep that, and you'll eventually just convert everything into graphite. So now, how does this work? So here we have in black the source rock, we have a sandstone above it, and we have a non-source rock shale sitting over the sandstone. And we'll just say that this area here is the gas window, and this upper area here is the oil window. So what type of accumulation you might see? So you start generating gas down here. This will feed up into this closed off structure. You have a shale as the seal, and you have a gas accumulation because the source rock is entirely in the gas window, even though the reservoir rock is sitting and the trap is sitting in the oil window. Now here we have, in terms of the fetch of this other structure, we have source rock in the gas window and some in the oil window. Those will migrate up into this and form an oil deposit with a gas cap to it. So this would be conventional exploration as you go and you drill these structures and you find your gas accumulation or gas and oil accumulations. You're drilling usually vertical wells, sometimes directional. In terms of shale oil and shale gas, you actually target more or less the source rock interval. So rather than looking for gas that has moved away from the source rock into a trap, you're going and drilling the source rock itself, where it is sitting in the hydrocarbon window. Now, how this works, we tend to drill these wells horizontally. Part of this is because the longer a well bore is in the reservoir, the greater the thickness of reservoir encountered by the well bore, the better production rate you have, and your economics is actually tied to that rate. To do this, we'll drill a vertical section. We'll then case off the vertical section, case in cement to keep the wellbore and the surrounding rock protected. And then you'll drill a horizontal section. Horizontal will be cased off as well. And then we need to perforate and fracture this. So first we perforate the first stage. You usually start from the end of the horizontal section. This would be called the toe, and this end would be called the heel. So you have the first stage perforated. You're firing bullets effectively through the steel to create holes. And then you pump high pressure fluid and sand down here, and which will go out into the rock through these perforations and fracture that first stage. This is then repeated for additional stages until you've completed the entire well. Now, when you hear people talk about the shale revolution, this is pretty much what you're talking about. If you go back to January 2006, where shale production had already been going for about 6 years, you're still down near zero. It was only a small fraction of total U.S. production or of conventional production. So non-shale production actually started decreasing over time, and shale really started shooting up. By 2017, shale production crossed the non-shale production, And since then, it has continued to climb, dip here for COVID. Conventional production did decrease until about 2020, but has been coming back since then. But if it's a revolution, it's a revolution that was 200 years in the making. The first gas produced from a well in the United States was in 1825. It was in Fredonia, New York, and it was producing from a fractured shale. And this is actually a photograph of the well here, this hole in the ground. And this stick-looking thing here is actually a bamboo pipe that they use to take the gas out and feed it into streetlights. In the same area in 1847, another well was drilled, and this is an actual photograph of that well being drilled. It did not flow gas the way they expected it to, so they did the first fracture stimulation by dropping 8 pounds of gunpowder down the well and exploding it. After that, the well flowed as expected. 1863, we get first gas production in Kentucky, is again a fractured Devonian shale. And then throughout the 1860s, you started seeing fracture stimulation of oil wells in various areas. Now, these use nitroglycerin rather than gunpowder, and there were apparently some very spectacular failures. Unfortunately, we don't have any photographs of those. Moving up to 1881, production from the fractured Pier Shale, sourced by another shale called the Niobrara in Colorado. In 1924, we had the first Niobrara shale production in Colorado. This was from a naturally fractured shale again. In 1926, the first Woodford shale gas production in Oklahoma. 1929 saw the first horizontal well drilled. This was in Texas. It was not an easy thing to do, and they really did not come back to this until the 1980s. Moving up, we jump all the way to 1947, and this was the first sort of hydraulic fracturing test. The fluid here was napalm. This was done by a company called Staniland Oil, which later became part of Amoco, and it was done on the Hugoton gas field in Kansas, which was a carbonate reservoir. In 1949, Staniland patented this process and licensed it to Halliburton, but using diesel rather than napalm. In 1953, we actually saw our first shale oil production. This was from a fractured shale in the Bakken Formation in North Dakota. 1960 was our first reported production from the Eagleford Group. This is in a subbasin called the Maverick Subbasin near the Texas-Mexico border. And hit the 1970s, and the oil embargo spurred research in the shale and other unconventional resources. The predecessor to the Department of Energy was funding a lot of research to figure out how the U.S. could produce more oil. So I'm going to follow two different sort of parallel timelines here that go through the 80s into the 90s. The first one, we'll start with 1981, Mitchell Energy drilled and fractured the first vertical Barnett shale well. This is the picture of the shale well here. By 1985, they had started what they called massive gel-based fracture treatments in the Barnett to increase the amount of production they were getting per well. In 1998, they switched to slick water fracs, so water-based rather than gel-based. This gave them effectively the same amount of production, but was much more economic. Now we're going to go back to the early 80s. We saw improved downhole motors for drilling that made horizontal drilling commercially viable. In 1987, Meridian Oil completed its first horizontal in the Bakken Shale. This led to a small boom in the Bakken, and also you saw a similar boom in the Niobrara. But these were hit or miss. If you had the right kind of natural fractures, they would work, but a lot of times they did not produce as expected. And in the mid to late 90s, Laco Energy drilled a number of vertical pilot wells to test this middle Bakken dolomite interval in Montana. The idea was that this particular interval had a lot more porosity and permeability than the rest of the Bakken, so what can we do with it? I do want to mention now, we have this horizontal boom and these hydraulic fracturing going on in the Bakken, but at the time you could not do hydraulic fracturing on a horizontal well. The technology did not exist. Now, LICO, recognizing this, partnered with Halliburton, and they came up with the technology to do a hydraulic fracture on a horizontal well. And this was first done in 2000 in the Bakken play in Montana, and was to discover the Elm Coulee field, or first production from the Elm Coulee field. In 2002, Devon Energy, who by this point had bought Mitchell, tested horizontal wells with hydraulic fracturing in the Barnett. The results of these two things, the Bakken and the Barnett, led to then the methodology spreading out to plays all over the United States. And it didn't stop there. In 2021, we saw the first well in the West Haynesville play. This is an offshoot of an existing play, but in a different basin or different sub-basin. So what I'm going to do now is just run through some information about the main shale plays in the United States, give a description of them, what kind of rocks they have, and a little bit about production. Now, there's a number of different U.S. shale basins. These are colored by the age of the shale that is producing in the basins. The Appalachian, Arkoma, Anadarko, Fort Worth, Permian, Williston basins are all producing from Paleozoic shales. The rest are producing from Mesozoic shales. The lighter green are Cretaceous, and this darker sort of green-blue is a Jurassic. I do want to point out, though, that while in some cases the basin that the shales were deposited in are the modern basins are producing from, in other cases, such as the Anadarko, Arkoma, and all of this Rocky Mountain basins, the basins themselves formed after the shale was deposited. So the shale is older than the basin. And we're going to start going up through the geologic column, starting with the oldest. So in the middle Ordovician, we had a island arc colliding with the edge of the Laurentian continent. This formed the Taconic Highlands, this first stage of the Appalachian Mountain development. And we developed a foreland basin behind that. And we had the deposition of the Utica and Point Pleasant formations in this foreland basin. The Utica Point Pleasant play exists primarily in Ohio, but also in Pennsylvania and West Virginia. I do want to point out that all of these will have these wells highlighted in different colors. The color is related to the gas-oil ratio of production in the first year of production. And what this is being used for is a proxy for what is the phase in the reservoir itself. So if it's red, which is greater than 50,000 cubic feet per barrel, that indicates a dry gas in the reservoir. Yellow, which is between 3,000 and 50,000 cubic feet per barrel, indicates a wet gas in the reservoir, and green actually indicates an oil in the reservoir. So you can see for all of these plays, they're done the same way, so it's going to have the same distribution. Now, the first production in the Utica play was actually in Quebec in 2008. However, there was a hydraulic fracture moratorium in 2012, which ended the play there. In 2011, Chesapeake Energy completed 4 wells in Ohio, starting the play in the U.S. So you can see from the map, we have gas to the east, increasingly liquids rich to the west. The Point Pleasant Formation drilling target, but the play is often just... So the Utica, and this is a series of well logs. If you don't know what a well log is, which you may not, these are electric response logs that are run on oil wells so that we can see what's in the subsurface. So over here we have a gamma ray log for the main part. And so it's just reading the gamma ray response. As you move to the right, it tends to be more shaley, that is higher gamma ray. To the left is lower gamma ray, which tends to indicate carbonates or sandstones. And over here we have a density in neutron. As they get close together, it indicates usually often hydrocarbons. And this one right track here on this one is a total organic carbon. So you can see where the organic rich sections are. So the Utica is a calcareous shale. That means it's got a lot of carbonate in it. Total organic carbon, or TOC, tends to be 1 to about 3.5%. The underlying Point Pleasant has interbedded limestone in shale. The limestone makes it a little bit better for fracturing. It's a more competent rock than the clay. And because of that, this is the preferred target. The upper member of the Utica is organic poor, so they don't really focus on that. They go for this lower member, which has 3 to 8% organic carbon. And these are boxes of core taken from the Utica. So you can see this is the Utica shale. In white, we have the percent carbonate. And in yellow, we have the percent of total organic carbon. So you can see the Utica has decent total organic carbon. The upper Point Pleasant, which is really black, which people tend to think of means organic rich, but in this case, it is not. This is generally less than 1% TOC. And then over here, we have the lower Point Pleasant with carbonate getting up to, 30, 40, 50%, and still about 2 to 3% organic carbon. Moving up into the middle Devonian, we have the microcontinent Acadia, which includes parts of modern-day France, crashing into the eastern margin of Laurentia, forming the Acadian Highlands in the second phase of the Appalachian Formation, or Appalachian Mountain Formation. And we have renewed Foreland Basin, and we see the deposition of the Marcellus Shale in this. The Marcellus is primarily in Pennsylvania. It does extend into West Virginia and very slightly into Ohio, but there's some changes in composition as you move over in Ohio. It becomes less shale. 2003, a company named Range Resources drilled an early Silurian target, so an older target, which may not have worked out, but they did see significant gas shows in the Marcellus. Shows just being you're seeing gas flow into the well as you're drilling through that interval. So by 2007, Range began commercial production in the Marcellus. It's primarily dry gas with some liquids towards the western edge. This is another set of well logs, and here we have gamma ray resistivity. So high resistivity often indicates hydrocarbons. And then again, we have the density and neutron porosity. So in general, the Marcellus Shale, which is this interval here, and I've blown it up over here, is 2 black shale intervals that are separated by a sequence of mixed limestone and shale. This limestone can act as a frac barrier, which means that you can actually, in some places, get 2 wells in the same vertical section, or stack vertically, or wells stacked vertically as well as horizontally. It tends to be the most clay-rich of the productive shales. As I said, clay is not necessarily a good thing for trying to create a fracture. It deforms plastically, but there are some areas where the Marcellus gets up to 65% clay. TOC is variable, ranges on the order of 1 to 20%, is also considered one of the more organic rich shales. And here we can see different intervals in a Marcellus core. So this is a box of core with 5 different sections. The ones highlighted in red are a silty mudstone, clay-rich mudstone. Green is organic-rich mudstone. and blue is a carbonate concretion. You can see also that you need to really do some analysis to be able to distinguish out, a silty mudstone from a organic mudstone, because just looking at them, even were you to have a thin section, you're often not going to be able to tell what it is. Moving from the Middle Devonian up into the Late Devonian, we have deposition of the Woodford Shale along the southern margin of Laurentia. This is deposited really in a passive margin setting. We have an embayment here in Oklahoma where we see the Woodford deposited Oklahoma into Arkansas, and it's also deposited out in West Texas and New Mexico. So in terms of production from the Woodford, it's primarily in Oklahoma, but also in the Permian Basin, that is the Midland and Delaware basins, also in this central basin platform. The producing basins in this case were all formed after the Woodford was deposited. So at the time, it would have been more or less a belt something like this, and then again continuing out in this direction. Woodford production goes back to 1926. The modern Newfield or Woodford played open when Newfield Energy drilled this in the Arkoma Basin, trying to follow on what was being done in the Barnett. The first well was drilled in 2004 and the first horizontal in 2005. By 2007, the price of gas was a little bit low, so they started switching over to liquids-rich areas with Devon and Energy opening up the Canna play and the Woodford in 2007. The Permian Woodford's been receiving sporadic interest. More than half of the wells that have been drilled out here were drilled in 2018, 2019. There's still a few companies drilling wells every once in a while. The Woodford Shale tends to have a very high gamma ray response. It's very radioactive. Gamma rays measured in API units. This log goes from 0 to 1,000. A typical well log that you will look at, your standard, would actually stop at 200. And you can see that the gamma ray would be off track in any kind of sort of typical log display. It does average sort of really high in carbon, about better than 6% TOC. Individual samples can hit as high as 30%. In Oklahoma, it's informally divided into 3 members. You have an upper member where you get this big gamma ray break, and then you have this lower member which has sort of lower gamma ray, and then the middle is just what's sitting in between. So there's 3 main lithologies: silicious black shale, carbonaceous black shale, and chert. The chert is really concentrated in these upper and lower members, is not so much existing in the middle member. The upper member in particular is chert rich, with chert increasing to the south. And if you go far enough south, the entire shale unit becomes a chert. You see similar lithologies and log patterns to this Oklahoma section. When you look at the Permian Basin, you can almost say, okay, I'm going to take this and say this is the upper member, and it correlates over to this same area here. And then moving up late Devonian to early Mississippian, the Bakken Shale was deposited in the Williston Basin. The Williston Basin is an intracratonic basin that has really an uncertain origin. Even the chair of the Department of Geology at the University of North Dakota says nobody knows how it formed. I think there's probably a couple of different things out there, but there's no certainty on it. This was the first shale oil play rather than shale gas. So it's primarily oil, but it does get gassier towards the center of the basin. In part, this makes sense. This is a structure map on the top of the Bakken Shale. And what you're seeing is that it's dipping down. So the lowest point's in the center of the basin, and it gets shallower as you come out. So it's buried more deeply in the center. So it would be hotter, and you tend to have higher gas because it's hotter. And the lower Bakken are organic rich ones. So that's these sections you can see on this log here highlighted. I hope I didn't drop off too much. I just got a note saying my internet was unstable. Anyhow, this is the upper Bakken here. This gray interval here is the lower Bakken. These are the source rocks, the organic rich mudstones. So the middle Bakken and the Three Forks Formation, which is just beneath the lower Bakken, are the primary producers. The middle Bakken is a mixed siliciclastic carbonate system. In the Elm Coulee field, which was the discovery where the first horizontal well was hydraulically fractured, it's a fractured dolomite, but generally it's laminated siltstone and sandstone facies that are the best middle Bakken rocks for production. The upper Three Forks is a silty to sandy dolomite, has dolomitic siltstones and some organic ore mudstones. Unlike the middle Bakken, which was marine, this was deposited in sort of marginal marine tidal flats and sabkha, or sort of evaporitic environments. So here we have the upper Bakken being the black unit in here, so the organic rich shale, and the lower Bakken similar. The middle Bakken is more variegated, different rock types. This is the mixed siliciclastics and carbonates, and then a similar in the upper Three Forks. So these are the parts of the system that produce, and these are the parts that are generating oil. Moving on in time up into the late Mississippian, we still have a passive margin on the southern margin of Laurentia, although we do have the leading edge of Gondwana land approaching. And we have shale deposition along this entire margin. And there's three different shales that are called in here, although really it's one continuous sort of, it would have been one continuous area of deposition. So the Barnett Shale in Texas, the Caney Shale in Oklahoma, and the Fayetteville Shale in Arkansas. So in the Mississippian shales, the deposition predates the current basin formation. As I said, it would have been really one sort of big band of shale deposition across here. The Barnett Shale is the original shale play or shale gas play. In the Permian Basin, the Barnett interval has been fairly active. 34 wells were drilled last year in this play. The Fayetteville Shale in the Eastern Arkoma Basin is correlative to the Barnett. This was the second shale gas play to open up, first drilled by Southwestern Energy in 2004. The Caney Shale in Oklahoma is also equivalent, but tends to be more clay-rich, has had poorer production. Now, in the Ardmore Basin, they have better success because they're drilling in interbedded siltstones and carbonates, and it's not simply clay. So looking at these shales, here's the Fort Worth Basin Barnett. We have siliceous mudstone, argillaceous lime mudstone, argillaceous lime packstone, a form of limestone. A gradational to the northwest into a shallow water chapel limestone, and it's locally separated into these upper and lower members by this Forestburg limestone. But where the Forestburg does not exist, because it's a fairly limited area where the Forestburg exists, it's not separated because there's nothing to really distinguish the upper and lower. In the Permian Basin, the Barnett overlies a limestone. You can see this Mississippi lime down here. It grades into a limestone as you go up into shallow water to the north. So you have an upper sort of carbonate-rich mud rock and a lower, more siliciclastic-rich mud rock. So these two, the upper and lower, are split on gamma ray, and then this lower can be divided into 5 intervals based on the resistivity response. Moving to the east in the Fayetteville Shale, this is in the Eastern Arkoma Basin. It's a black fissile, locally a calcareous mud rock like the Barnett, it grades into limestone as you go to the north, and the lower part of the Fayetteville is the main drilling target. The Caney Shale, moving now back towards the Barnett, you go to the Arkoma Basin. This is an upper zone of mudstone with some interbedded siltstone down here. And then the lower zone is primarily fissile mudstone. So you can see this symbol here is showing the areas that would be perforated and produced from. So a lot of it is focused on the siltstone facies. When you move into the Ardmore Basin, the upper part of the Caney may contain limestones as well as siltstones. And overall, the Caney here is thicker than it is in the Arkoma Basin. Again, the best production for both basins is from interbedded limestones and siltstones. Now I'm going to back off of talking about shales to talk about the basin. So by the middle Pennsylvania into Laurentia to form Pangea. So you have the last stage of the Appalachian Formation over here, the Alleghanian orogeny. And then as a continuation of that, we have the Ouachita Mountains in Oklahoma and Arkansas, and then the Marathon Fold Belt in Texas and Mexico. So we have the Arkoma Basin, the Fort Worth Basin, and down here the Valverde Basin, forming as foreland basins to this thin skin fold and thrust belt. But we also have a number of basement chord uplifts and steeply faulted basins, the Delaware Basin, the Midland Basin, the Anadarko Basin. Out here, this is a Paradox Basin in Utah. These may be related to this deformation here, but there's a school of thought, and it makes a somewhat sense that this is actually coeval deformation related to convergence along the western margin. The problem is very little of the Paleozoic western margin exists anymore. It's all been either faulted away or covered in volcanics from during the Mesozoic and Cenozoic. Moving up into the early Permian, one of the things to see is many of these basins have now filled up, and we have really the only area we have connection to open ocean is out here in West Texas and New Mexico, and we have deposition in the Delaware Basin, in the Midland Basin, and this is the Wolfcamp, Bone Springs, Sprayberry formations. So on the left here is the Wolfcamp A through D. On the right, this is showing the Bone Springs in the Delaware Basin and the equivalent Sprayberry in the Midland Basin. You can see that for the most part, these are oil plays, although there is increasing gas to the west in the Delaware Basin. This is some work I'm stealing from one of the people who works for me, just showing type logs for the Delaware Basin in New Mexico and Texas and the Midland Basin. You have this lower part of the Wolfcamp that has mixed siliciclastics, a little bit of carbonate, more so in New Mexico where you had some closer to the shelf edge here. These are basinal in general. This section is really complicated because we had active faulting going on and rapid sea level changes due to glaciation. So there's a really complex interplay of faulting and sea level change that gives a fairly complex sequence in here. By the time we get up to this Wolfcamp A, the active faulting has largely stopped. Sea level changes are still happening, but they're slower. So we have these areas with high carbonate content where the sea level was high and high sand content where sea level was low. And that sort of repeats across the basin, and you can track these out. So this here we have, again, the Wolfcamp D coming up through Wolfcamp A, and then this younger section here, which has the Bone Spring Formation, and then the Dean, Leonard, and Sprayberry in the Midland Basin. To match these up, the blue shows just hydrocarbon production in millions of barrels of oil equivalent. So we have almost 6 billion barrels of oil equivalent coming out of the Wolfcamp A. In the Delaware Basin, the blue is for Delaware, the sort of brown is for Midland. So the Wolfcamp A is the main producer in the Delaware Basin, followed by the second Bone Spring Sand. In the Midland Basin is the Wolfcamp B, followed very closely by the Wolfcamp A. So all of this Paleozoic has been about the formation of Pangaea and various things agglomerating onto the Laurentian microcontinent. When we move to the Mesozoic, we get more about the breaking up of Pangaea. So we've already, by the late Jurassic, started forming the Atlantic Ocean, and we have rifted off the Yucatan Peninsula to form the Gulf of Mexico. Now, as Yucatan rifted off, it left behind a very complex margin with high areas like the Sabian Uplift and low basins. And it's in this basin here behind the Sabian Islands that the Haynesville Shale was deposited. So really we have two different depicenters of the Haynesville, one here in what's called the Sabian Uplift Basin, and the other in the East Texas Salt Basin. In the East Texas Salt Basin, it is generally too thin to be much of a target for drilling. So our core area of production is over the Sabian Uplift. In 2004, KCS Energy was drilling a well targeting something deeper, ran into gas shows in the Haynesville section. For the next couple of years, several operators were drilling vertical wells to test and core the play. And in 2007, Chesapeake Energy drilled the first horizontal. So this is really a very dry gas play. There's only very minor liquid volumes reported. This off to the west, this West Haynesville play was first drilled in 2021 by Comstock Resources. This is very deep, high pressure and high temperature. It remains to be seen just how well this play is going to work. The Haynesville Shale is an organic, rich, carbonaceous mudstone. There's three different facies, and I'm not going to talk about these too much, but effectively a siliceous mudstone with little round things in it. The most common is this laminated mudstone that may also have the piloids or little round things effectively, and then a bioturbated calcareous or siliceous mudstone. The overlying Bossier Shale tends to have lower carbonate content and generally less organic matter, but is still productive in some areas. In the late Cretaceous, we have a combination of things taking place. There's a foreland basin forming in the mid-continent. I'll talk a little bit more about that in a second. But we have this high sea level rise, highest global sea levels that we've seen in the Phanerozoic. And it's in here that the Eagleford Formation was deposited in a somewhat sheltered coastal or shelfal area. Now, we're going to go a little bit off on a tangent here. There's a story that's been around in the oil industry about how Petrohawk Energy discovered the Eagleford play in 2008. The origins of the Eagleford are a bit more complex than that. From 1960 to 2003, there were 12 wells that reported production from the Eagleford. Most of these are in this area here near the Texas-New Mexico border, called the Maverick Subbasin. Although there were some further up to the northwest, or northeast. All of these had targeted deeper zones and produced from deeper zones, but they had seen gas in the Eagleford, and at some point they completed in there and produced gas from it. In 2005, Burlington Resources was drilling a well targeting a lower Cretaceous target, but encountered gas in the upper Cretaceous. The lower Cretaceous target didn't work out. The engineer on the play or on the well, excuse me, suggested, why don't we just frack that section and see what it does? They did, and it did flow gas. And so then it became a question of what is it? We found something and it wasn't what we were looking for. What have we found? It was at this point that I got involved. I was working in a different group. I was pulled in to help out the geologist that had worked the well, figure out what it was. I would love to say that I then discovered the Eagleford play, but that is not what happened, because right about that same time, Burlington Resources was bought by ConocoPhillips, and I handed off all of this work to another geologist named Paul Basinski, and he ran with it. So in 2006, ConocoPhillips drilled a second well in the same area. They cored it, and they also put the initial well on production. In 2007, ConocoPhillips drilled 2 more wells in the same area. One was a pilot hole that had 3 sidetracks. Down in the Maverick subbasin, a company called TXCO drilled 2 wells, 1 vertical, 1 horizontal, targeting the Eagleford and the Maverick subbasin. 2008, by August 18th, ConocoPhillips had completed one of the sidetracks over here as a producer. TXCO had started drilling 3 more wells. Espada Operating drilled 2 more, and Texas Cornerstone did 1, excuse me. And Texas Crude, who was Burlington's partner on the original well, started drilling another well over here. I say by August 18th because on August 19th, Petrohawk drilled the discovery well. Now, to be fair to Petrohawk, they did look at the play and picked a good location. And they were also the first company to actually go into production mode on this. Many other companies were waiting for the price of oil to come back up because in 2008 it had crashed a bit. So production in the Eagleford goes from slightly north of the San Marcos down into this Sligo and Edwards reef margins. The area between the 2 reefs is the dry gas part of the play. The Eagleford is a mix of oil, gas condensate, and dry gas. It does continue into Mexico. It was tested by 5 horizontals in 2010 to 12. Up to 30 shale wells were drilled in Mexico by 2015, not all in the Eagleford. But there's been a hydraulic fracturing moratorium since 2019. So west of the San Marcos Arch, the Eagleford ranges from marls to limestone. So this is a fine-grained carbonate to a coarser-grained carbonate. So the marls are the organic rich part, 2 to 7% TOC. They have abundant shells of small shells and planktonic forams. The limestones tend to be largely planktonic forams, but have lower organic content. As you go east of the San Marcos Arch, there's increasing clay content due to sediment coming from the Woodbine Delta that existed in that area. The Eagleford can be divided into 2 groups. The upper Eagleford, which has lower gamma ray and lower TOC, and then the lower Eagleford, which has higher gamma ray and higher TOC. The upper is generally thin, but it thickens significantly as you go to the Maverick subbasin. Slightly younger, we have deposition of the Niobrara Shale. So here we have the severe mountain belt forming in Colorado, Utah, or sorry, Arizona up into Utah. And we had the Foreland Basin developing here, and we still had the high sea level rise. So the combination of this 2 gave us this Cretaceous interior seaway, and the Niobrara Shale was pretty much deposited across this entire area. What happened to make some of it prospective was that in the Paleocene, we had the severe orogeny. This was unlike the thin-skinned severe, the laramide orogeny. This gave us high angle basement core uplifts with significant basins, and it's these basins where the Niobrara got buried deeply enough to start generating oil. This is the Denver Basin, the Raton Basin here, the Powder River Basin, Green River Basin, and the Piceance and Uinta Basins over here. First Niobrara production was in 1924. Most of the production is in the Denver Basin. There's actually about 9,000 wells in this basin compared to about 900 in the Powder River and about 90 in the North Park Basin here. So it was developed at Wattenberg Field in the Denver Basin starting in about 1985. It's long been recognized as a tight reservoir that could only produce if you had natural fractures. They began drilling horizontal wells and hydraulically fracturing them around 2008. Two peaks in this, 2014 right before a price crash and 2019 right before COVID. Again, production's mainly from the Denver and Powder River basins is largely oil. The Piceance and Green River basins tend to be more gas-rich. The Niobrara is composed of interbedded chalks and organic-rich calcareous mudstones or marls. The marls have the high TOC and clay content, so they would not produce well. The chalks still have high, about 2 to 3% TOC. So you're going to want to try to produce out of the chalks, but you're getting organic material out of both. The clastic content increases to the west as you get closer to where the mountain belt was at the time of deposition. In the east, the Niobrara is underlain and overlain by non-calcareous shales. Locally, as in this thing here, there is a intervening sandstone at the base, the Codell sandstone. To the west, the Niobrara intertongues with and grades into the Mancos Shale. So some common characteristics, all of these things are deposited in semi-restricted basins, but they tend to also have access to open ocean. So the semi-restricted allows you to get conditions that will preserve organic material, but the access to open oceans allows you to bring in the nutrients that gives you that organic material in the first place. Production's generally from more brittle interbeds, carbonate, siltstones, and cherts, and not from the pure shale itself. And even the shales tend to have less than 40% clay volume. So are they really actually shales? It's one of the reasons we tend to call things mudstones rather than shales. Now, there are differences within plays and also between plays that do impact the productivity that you see from these different reservoirs. So talk a little bit now about resource and production. This is a map showing remaining resource, technically recoverable resource, and production. So the size of the bubble and the number on the left is the remaining or the technically recoverable resource in billions of barrels of oil equivalent. I didn't explain this earlier, but a barrel of oil equivalent is a way to combine both gas and oil and compare them directly. Effectively 6,000 cubic feet of gas is equivalent to 1 barrel of oil in terms of the energy it would generate. So you divide the gas by 6,000 and add that into the oil. The red part of the wedges are the remaining gas in the play. The yellow part is what's been produced already, and the green is the remaining oil. So you can see that most of these plays still have significant amounts of remaining resource. Now, this is technically recoverable resource. Not necessarily all of this is economically recoverable, but economically recoverable changes on a daily basis. And over time, what was not economically recoverable a year ago can be economically recoverable later. Technically recoverable also tends to change over time. 40 years ago, none of these things would be considered technically recoverable. So these numbers may also increase. Now I want to look at oil production, and I'm focusing on oil production from horizontal wells in different plays. So here we talked about the Utica, the Niobrara, and the Woodford. Really, in terms of total shale production, these are pretty small. Compared to here, we have production from the Bakken. You can see it increasing. There was a price crash in 2015, 2016. It started to recover, another dip for COVID, and it came back, and it's sort of held steady, maybe with slight increase in the last year or so. You see a similar pattern in the Eagle Ford, although the crash or the drop in production was more significant back in 2015. And then we have the Midland Basin and the Delaware Basin. And if it weren't for these underlying things here, you would see that these pretty much, other than for COVID, have just continued to increase over time. They didn't have even a drop really for this 2015 price crash. So 63% of shale oil production is from the Permian Basin, and 75% is from Texas. And shale oil production is approximately 60% of total U.S. oil production. Looking at gas production from horizontal wells, we have the Barnett Shale, the Fayetteville. Both of these have been tailing off. Haynesville, we have a peak around 2012, and then it drops off and comes back, and I'll talk a little bit about that in a minute. The Marcellus has just been increasing over time. The Utica, similar. And then I'll throw this on. This is gas production from oil plays. And this is a problem for these dry gas plays. So if you look at this Haynesville production here, it increased up until about 2012 when we started seeing significant gas coming from the Eagle Ford. Eagle Ford production is based on oil price. Haynesville production is based on gas price. This two separated around this time. Gas got very cheap because there was so much of it on the market, and you couldn't afford to keep drilling in there. So it dropped off, and it was only once we got the ability to export liquefied natural gas in 2017 that it started increasing production again. And it started tailing off more recently as these West Texas oil plays start producing more gas. So 40% of shale gas production is from oil plays. 23% is from the Permian Basin, and better than 38% comes from Texas. And shale gas actually makes up about 70% of total U.S. gas production. This is a map of gas fraction over time. I'm going to sort of ignore most of these plays up here, although I will say the Woodford shown here looks more like a gas play than an oil play. But for many of these oil plays, the amount of gas that's being produced is increasing over time. This does tend to be from just pressure depletion in the reservoir as they're producing. If you look at the first year production for these various plays over time, the amount of gas that's coming out relative to the amount of oil is still about the same. So it's not that they're drilling in worse places. It's just that over time, all production tends to get more gas rich. One of the other things is water fraction. So this is water over total production. You can see that for the Delaware Basin, the Midland Basin, these are pretty high. It's also high in the Barnett, but the Barnett has fairly low production relative to these. But in the Permian Basin, you're producing about 9 million barrels of, 9 million barrels of oil a day, and about 14 million barrels of water a day from this. And it's actually getting rid of that water that's probably one of the biggest threats to continued production in the Permian Basin. In summary, shales moved from a minor contributor to the dominant source of U.S. hydrocarbon production. This is largely due to technological innovation. Reservoirs were deposited in a variety of basin types, but generally semi-restricted basins with some access to open ocean. The regional extent of plays gives you changes in facies, which impact the productivity potential. Resources are significant, with technically recoverable resource estimates in excess of 100 billion barrels of oil and 2,000 trillion cubic feet of natural gas. Production has generally been on a commodity price and demand. Increasing water production is a significant challenge in the Permian Basin, and increasing gas from oil plays is the largest challenge facing the dry gas plays. This was the link to the paper I mentioned, and thank you.
So anyway, I'll read the first question, which is from Mary Helen. Both the gas and oil production graphs showed sharp dips in approximately March 2021, a full year after the COVID hit. What was the cause of that?
Oh, what was the cause of that? I believe there was a bit of a price crash right at that point in time. It was just a very temporary. And I think it may have. Yes, sorry, I'm just going back to look at that. I haven't really focused on that particular one. I think that was around a point in time when we saw pipelines were having some trouble, and so there was local inability to move products, and prices were going down, and people had to shut in.
Okay, thank you. Anybody else have any questions? I'm not seeing anything. I'm going to look in chat here. So I do have something in. It's going to be. I can. Okay, well let's go back to Joe right here. The available oil/gas appears to be very good. How does this compare what is thought to be available in Alaska and the Middle East?
Okay, so I'm going to just talk in terms of proved reserves as far as the Alaska goes. Right now, in terms of oil, Texas and New Mexico have the highest proved reserves, and that's all Permian Basin, or mostly Permian Basin. Oil proved reserves in Alaska have been dropping. Alaska still has probably the second highest gas reserves, higher than Texas, or Texas first, Alaska second. And then actually Pennsylvania third with the Marcellus. In terms of the Middle East, it's difficult to say what they actually have in terms of proved reserves. I think the problem in the Middle East is, if they decide they want to just turn the taps on, they can do it. That's one of the issues is they do have huge reserves. I will say some of the areas are actually getting a little bit played out. For example, Saudi Arabia is starting to look at unconventional plays instead of just the conventional. And I was in Kuwait last year, and they're working on trying to do polymer floods to try to increase production. So some areas in the Middle East are getting played out, but they still have, a significant reserves, but I can't tell you exactly how that compares to what these numbers are.
Thank you. There's a few questions under chat, and we prefer to have the questions in the Q&A, but it doesn't really matter. First of all, there's a comment from Claude, and if you're interested in this, you're best off all of you are best off looking at chat because he's got a link address there. He says, my go-to for greenhouse gases already in the atmosphere, and then he has a link address there. If you're interested in that, go to the chat and copy paste it, I would say. And then we have a question from Dale. Can you explain how horizontal drilling is done?
Okay, I had covered a little bit about that, so let me back up and I'll share again here in a second. So this may not be what you're talking about, but we'll drill a vertical section, case off the vertical section that is, and you do this as you go along, you do it in stages, but you drill, you run steel pipe and then you cement it, and then you drill out and you do another section, run steel pipe and cement it. Drill out the horizontal section. So what they do is they have special motors that sit at the bit that allow you to turn the drilling direction. And there are tools that people use. And generally, you may have actual seismic reflection data to help you constrain exactly what the angles are or what the shape of the reservoir is. And what you're really doing is not necessarily horizontal, but you're trying to stay within a given zone in the target interval. So sometimes they may be a little bit slanted or they may actually undulate as you go along them. But you have this group of people that really just work very much on geosteering these wells. You then case that horizontal section off, again, steel casing cement, and then you perforate it. So they have what are called guns, and they actually you do use explosives and steel shots to penetrate the casing and the cement, which creates openings to the outside. Then you pump down high pressure fluid, usually with sand to hold the fractures open. So the fluid creates the fractures, and then the sand goes in to keep them from closing. And once you've done that first section out towards the end of the well, you come back and do it again and again until you've done the entire length of the horizontal well.
Okay, thank you. If Dale has any further questions, he can add them to Q&A or chat. The next question we have is also in the chat from Mark. It says, what is the complexity of getting rid of the water, or is it just pumped down into the ground?
Okay, so the water is usually just pumped down into the ground, but there are problems with this. So in the Permian Basin, there have been two ways that they've gotten rid of it. They've disposed of it in shallow intervals, often in intervals that had old conventional production. This has had two different sort of side effects, or maybe multiple, I should say. As you inject into this, the pressure inside the reservoir increases. So as that has happened, it has created actually a drilling hazard for wells that are going deeper. And the shale wells are all going deeper, so they're creating their own hazard to get through. There have been blowouts of old wells with injected water because they've been drilling in the Permian Basin for 100 years now. So in some cases, old wells that have been completed or abandoned now are starting to leak or even have geysers where they have injected water is coming up at, again, at higher pressure, and the well can no longer, the old abandoned wells can no longer hold that pressure back. They have also tried injecting into deep sections so that it doesn't come out. The problem with that is that it travels, these are often karsted carbonates. So you have cave systems down there. The water travels a long distance and it has started to actually lubricate some of the old faults that are out there. And they have had caused by lubrication of these faults that already had some stress on them. And it's that is an issue. It concerns people, although most of them are out in the area where only the coyotes will feel the earthquake. But that's the complexity is just the amount of water. You know, if 80% of what's coming out of your well is water, and you want to get, you know, people are talking about producing a billion barrels a day of oil, that's 80 billion barrels a day of gas, or of water.
Okay, and this water is pretty nasty stuff too, right?
It is, yes, it is not nice water. So, I mean, we have had discussions, because the regulator in Texas, the Railroad Commission, approached us last year, and some of the things we have set or we're talking about was, can you actually do clean it? And it seems to be the answer is you can get about half of it somewhat relatively clean. It depends on what you want to use it for, because you don't want to, even if they're after you clean it, don't want to do anything where it will then go towards human consumption. So you could use it perhaps for watering crops that are destined for something other than human consumption, that are not going to be eaten. But we're trying to figure out, or a lot of people are trying to figure out, what is it you can do? Because if you could get it down to half, that reduces how much you get rid of. But what do you do with that other half, even after it's cleaned? And it is expensive to transport water. Water is heavy. Whether you're trying to build a pipeline, which you need to have the pipeline, or truck it, or whatever it is you're doing.
Okay. Thank you. The next question is from Angie and Pete. Did the meteorite in the Gulf of Mexico that doomed the dinosaurs affect any of this geology?
Not really. That was sort of later than most of these things, sort of later than the deposition of any of these shales, and a little far away from the Rocky Mountain basins to have much of an impact there. On an interesting note, I saw something this week, or maybe late last week. They have found another piece, what they think is maybe another piece of that same meteorite, like they may have broke up, but off the west coast of Africa, there's another collision structure, crater structure that's just been discovered.
And that would obviously be the same time frame.
Yeah, they think exactly the same time. So one of the things, more obvious things is like Shoemaker Levy did when it hit Jupiter. It may have broken up into multiple pieces.
Interesting. I had not heard that. So far we have just one more question. No, actually there's two now. But we'll get this one from Joe. President-elect Trump often said, "Drill, baby, drill," as a means to drop prices for most things. Do we really need a great expansion in drilling, or would that be, or would that be and would that be cost effective for the industry?
Um, it's a difficult combination, the intersection of politics and business, right? Um, for industry, you don't necessarily want the prices to be incredibly low because these wells are expensive to drill. And the lower prices go, the less of your inventory is you're able to drill. So it's a sort of a side effect. As prices go down, drilling decreases, doesn't increase. So it's not really a cost-effective thing to do. Drilling a lot and dropping the price is sort of cutting your own throat. We've also been seeing that there's been a lot of, particularly since COVID, of capital conservatism in the industry, where people could be drilling more, but they're preferring to spend their capital on things like share buybacks and sending money back and sending money back to stockholders in various forms, rather than trying to spend it all on drilling. And I guess the third point I put on that, there's been a lot of consolidation of the industry in the last couple of years, particularly in the Permian Basin. And so when you have one company buy another company, the the new company is not going to spend the same amount of money that the two independent companies would have spent put together.
Okay, thank you. At this time, we have just one more question. Actually, I see another one come in, but okay, this is from Dale. You show a high density of drilling rigs in certain areas. How does this interfere with cities in those locations?
I mean, it's an interesting, it does not necessarily impact. What you tend to see is in more dense urban areas, you will see more wells drilled from an individual pad versus and longer wells drilled, so that they try to have fewer surface locations but still get the same coverage of wells. I may even, am I still sharing?
Not at the moment, but you can obviously go back to it.
Okay, because I can go find this. I have a slide, I think, or two that may show some of this that I had stuck in the extra area in the back. Oh, I didn't put those in here. I thought I had. But if you look out in the Permian Basin, where it's mostly desert and it's not even good ranch land for the most part, you may have, one or two wells drilled from an individual pad. Now that's been increasing, but if you go to the Barnett Shale, which is drilled like in Fort Worth and Dallas, you'll have 18 wells drilled from a single pad, and they'll be much longer and much more complex well paths to get out. Same kind of thing in the Marcellus, certainly in the towns. You don't actually see any drilling, though, in, say, Pittsburgh itself. There's a no drill zone, and then people drill around it. So I think it's there's usually not much impact. You see as much impact really in some of these things in California with these old conventional. I used to live in Bakersfield, and one of the houses I looked at had a pump jack in the backyard. So that was you just have wells in the middle of town. And parts of Houston, you do the same thing. And those are conventional rather than these unconventional wells.
Tim, Steve Erickson here. Has the number of vertical wells dropped, and what would be the percentage, say, of wells drilled be vertical versus horizontal? Is it 50-50, or what do you think is the approximate?
If you're talking onshore
Yeah.
US, I would say it's more like 90-10 horizontal to vertical.
So vertical is kind of going out onshore then.
Yeah, well, they're still being drilled, but they tend to be for smaller targets. It's the small independents, of which I was one, going out and trying to drill for 100 barrels here, 1,000 barrels there.
Yeah.
On old, often just trying to find an area where they didn't drill at the top of the trap, and there's still like 20 feet of column left.
Right. So is wildcatting, the old-fashioned guys going out and slamming wells in, is that kind of a thing of the past onshore now? Is it?
I would say onshore US it is. I mean, some of this stuff is still fairly wildcat, but a lot of it isn't. I did have one friend who had gone out and he put a group of companies together. They all pitched in and spent, I can't remember, like several $1,000,000 on getting a stretch of 3D seismic in an area that didn't have any. And then they drilled like a whole bunch of successful wells because do things like that. But for the most part, it's so covered that it's not a true wildcatting kind of thing where you're going out and testing something brand new.
For those of you who don't understand, wildcatting was the old-fashioned, when drilling had not been covered in a lot of areas, some people just put together a team and go out and drill a well. That they weren't even, in a lot of cases, oil companies, but just investors who would go out and put wells in, and some were very successful and some went broke. It was quite an interesting time period back 20s through the 1970s. Really was that time period, but it's the complexities of the wells were drilled in. Basically became kind of the realm of the oil companies had leased the land. Getting the oil leases as much as anything else problems, I remember correctly. Is that correct?
Yes. Yeah. That requires a special breed of person. Which there's a new show on. I can't remember. Was it
Landman?
Landman? Yeah. Was that Netflix? I can't remember where it was. So
Yeah,
there's
I
one
got
more
one more
question
question
there.
from Mary Helen here. Could some of the older / out of use wells be subsequently filled with solidified carbon as a method of sequestration?
Okay, so solidified carbon, no. There has been a lot of research into doing this with supercritical CO2. So when you put CO2 under pressure, it becomes supercritical, and that means it still has the density of a gas, but the viscosity of a gas, but the density of a liquid. So it's a really efficient way of doing it. Now, there are problems with doing this with existing wells in that CO2 is a very reactive component. It's bad for cement. It's bad for steel. So if you just go into a well, an old producing well, it won't meet the requirements that the government has for sequestering for, I think it's supposed to be, I can't remember, 200 years guarantee. In fact, a lot of times these older out of use wells are more danger as a leak point than a way of storing it. So people are now starting to go and say they're really looking for places that weren't drilled before. Originally, the idea was to go back and see if we could reuse these things, but it's more cost effective to drill a new well, and these older wells are often really more of a hazard than a help in that kind of thing.
I think we're going to wrap her up then for tonight. Thank you very much, Tim. Really appreciate you coming on.
There's a few more comments coming in. They're all just thank yous. Interesting talk. Very well done, informative presentation, and I would agree with them.
Thank you, Tim. Have yourself a good night.
Well, thank you. My pleasure.